Good morning. This is 5.6, properties of linear functions. So we're going to start with an activity of examining a few rectangles. So if we look at our first rectangle here, we can see that it's got a width of 1 and a length of 2. Our second rectangle has a width of 2 and a length of 3, so on and so forth. And it asks us to draw the next two rectangles in this pattern. So this one here is a 4 by 5, which means our next one should be a 5 by 6. So I have to make sure to go 5 across, 3, 4, 5, and 6 down. There we go. So our width is gaining 1 each time, and so is our length. And then our next one should be 6 across by 7 down. So those are the next two rectangles in the pattern. So use the information from these rectangles to complete the tables below. Another thing that it might be helpful to do here is to actually just label that this one was a 1 by 2, this one was a 2 by 3, this one was a 3 by 4, 4 by 5, this one we said was 5 by 6, and 6 by 7. That will actually help us out a little bit as we fill out these next tables. Okay, so this first table is asking us to compare the width to the area. So area is how many complete squares does it take to cover that rectangle. And so we have a width of 1 and an area of 2 because we have 1, 2 squares. The second one is a 2 by 3, which is 1, 2, 3, 4, 5, 6, an area of 6, and so on and so forth. As you can see, we can just multiply the length by the width to get the area. So on our next one, we would get 12, because 3 times 4, then 4 times 5 is 20, 5 times 6 is 30, and 6 times 7 is 42. The second chart is asking us to compare the width of the rectangle to the perimeter. The perimeter is the distance all the way around. So on our first rectangle here, the perimeter would be 1, 2, 3, 4, 5, 6. So it took us 6 steps to get all the way around. On our second rectangle, well, we went 1, 2, 3, 4, 5. If you think of doing half of the perimeter as making an L shape, we can take that 5 and double it to get a total perimeter of 10. When you look at the 3 by 4, if we'd make our L, that's 7. 3 plus 4 is 7, and then you would double that to get 14, and so on and so forth. Our next one is 18, then 22, then 26. How did I get 26 on this last one? 7 plus 6 plus another 7 plus another 6 takes us to the 26. So the next question is, which of these table of values represents a linear function? In other words, if we graph it, it's going to create a line. And so you may have a guess just by looking at the numbers. One of the things we can look at is that the width of the rectangle in each table is going up by 1 each time. So to get from 1 to 2, it's plus 1, plus 1, plus 1, plus 1, plus 1. On the second column here, we're going up by 4, then 6, then 8, then 10, then 12. Here we're going up by 4, then 4, then 4, then 4, then 4. So which one seems like it has a steady increase is the perimeter one. So I'm going to type that down as our guess, and then what we're going to do is check it when we graph. Okay, so which of the table of values represents a linear function? And we're going to say the second one, because perimeter increases by the same amount each time as the width goes up by 1 each time. Now we can't see that, so I'm going to make it a little bit smaller so that we can read that. Okay, pardon any typos here. All right, let's go ahead and graph this. Okay, so we're going to graph our information kind of need to see this table at the same time, so I'm going to be scrolling back and forth a little bit. Actually, I'm just going to zoom out for this question so we can see that all at the same time. So on the left, we're going to graph our information from the left. On the bottom, we need to go from 1 to 6. We've got lots of room here. So I think I'm going to say that every 2 tick marks is going to be a change in width. So we're going to say that's 1, that's 2, 3, 4, 5, and 6. That way it's nice and spread. I got lots of room. Along the y-axis, we need to go all the way up to at least 42. So I'm going to say we need to go up to about 50. So it seems like every 2 squares would have to be worth about 10 in order to get all the way up to 50. And this works out quite nicely. So notice that when I'm setting my scales here, it's like a ruler. So if 2 squares is worth 10, the next 2 squares has to be worth 10 again, etc. Here, 2 squares is worth 1. I just have to make sure I'm consistent along my axis. Okay, and we should also have some labels. So this is going to be area and that's in units squared. I'll put the square down there in a second. And on this one, it's going to be width. And that's in units. Our title, you can't come up with a good title. You can just say the y versus the x, or area versus width in this case. I just need to add my exponent here because it was a little bit tough to type it. So I'm going to go back to my pen and just make sure I have a squared on that for area. Okay, now I'm going to go ahead and plot my points. So my first point was 1, 2. So I need to go over 1 and up 2, which is barely above the axis there. Then at 2, I need to be at 6. Remember, that's 5, so 6 would be just above that. 3 and 12. And I'm just doing my best to estimate here. 4 and 20, well, that's an easy one because I can see exactly where the 20 is. 5 and 30. And then I've got 6 and 42, which is about here. Now it looks kind of like it might be linear, but it also kind of looks like it might be a curve. So what I'm going to do is graph my next one and see which one looks more linear. And then I'm actually going to use a straight line and see which one actually makes more of a straight line. Okay, so on our second graph, once again, we want to go all the way up to 6 on the bottom. We're going to do perimeter on the side. We need to go up to about 30, but I don't want to use 3 squares to equal 10. I just find that's very awkward, dividing things up into 3. So I'm going to stick with each square being worth 5. It's actually more reasonable. I don't usually recommend going up by 3 of something. It's terrible for estimating. Okay, and we're going to do a few labels on here. So this graph is going to be perimeter versus width. And so we've got width in units. Didn't say what the units are, so we'll just put a U for units. Sometimes if it tells you it's centimeters or whatnot, you can actually put that. And this is perimeter in units again, and I'm going to rotate it. Most of the time we do label it like this, so that's a little bit easier to see. And I could have done that here too, but I'll just leave it for now. Okay, so let's go ahead and plot these points. So we've got 1, I'll go back to my pen. We've got 1, 6, so that would be about here. We've got 2, 10, that's an easy one. 3, 14, 4, 18, 5, 22, and 6, 26. So looking at these two graphs now, which one looks more like it's going to make a straight line? Seeming to look like the second one. It makes more of an even staircase. If you're thinking about climbing this staircase, it seems like the stairs are getting further apart the further you climb, which means the staircase is getting harder and harder to climb. Here, if I go ahead and draw my line, there we go. It fits on here quite nicely. Here, if I start to draw my line, it doesn't really work. Doesn't really work if I go like that, so I can't use a line tool. What I'm going to have to do on the first one is sketch a kind of a connect the dots pattern as best I can, which ends up making a bit more of a curve. And I would suspect that the further we would go along that graph, the curvier it would look. Okay, so that is the difference. So we were correct. The second one is actually the linear graph. It went up by a steady amount. Think about a staircase. As you climb up a staircase, you don't want the stairs to get further and further apart or change on you. You want the stairs to be consistent. All right, so I'm going to zoom back in here just so we can see a little bit bigger. We're going to go on to example 1. The cost for a car rental is $60 plus $20 for every 100 kilometers driven. Identify the independent variable and the dependent variable. Well, these two titles here are our variables. And generally the first one listed is going to be our independent, and the second one listed is going to be our dependent. Now, maybe somebody lists them in the wrong order though, so we do have to think about it. Does it make more sense to say that the cost depends on the distance you traveled, or the distance depends on the cost? And it is true that the cost would depend on the distance. So that's how we know it's the dependent one. It depends on the distance. So the independent variable in this question is distance, and that's in kilometers. So we should always include our units. And the dependent variable is cost, and that's in dollars. So represent this relationship using a table of values, at the right. Okay, so let's go ahead and start filling this out. So the easiest to start with is almost always 0. So if you travel 0 kilometers, how much would it cost you? Well, the rental itself still costs you $60. If we went 100 kilometers, let's make it easy. Let's go the even 100. Then we would have to go up by $20, which means we would have a cost of $80. If we went 200 kilometers, that means we have to go up another $20. So now we'd be at 100. If we went 300 kilometers, we'd be at $120 cost. And if we went 400 kilometers, we'd be at $140. Now notice I didn't put dollar signs or kilometers next to all these numbers because it's listed in the title. So therefore I don't have to write it every time. Now it asks us to represent it as a set of ordered pairs. So I'm going to go ahead and type that so it's a little bit easier for people to read. I'm going to have to go a bit smaller here. So as a set of ordered pairs, I'm going to start with my curly bracket to say that I'm about to list a set. And my first set would be 0 kilometers, and that would be $60. So there's my first ordered pair. Then I put a comma, and my next ordered pair would be, if I went 100 kilometers, that would be $80. Remember, we did ordered pairs in a previous section. My next one would be if I went 200 kilometers, that would be $100. And then if I went 300 kilometers, that would be $120. And then 400 kilometers, there we go, would be $140. And then I put my curly bracket on the outside to say that my set is over. So it's a set of a bunch of ordered pairs. Now we're going to represent it as a graph. Again, I'm going to zoom out here so we can still see our table of values when we go to graph. Okay, so what's going to go along the x-axis, which is the bottom, is always going to be our independent. So that's going to be distance along the bottom and cost along the side. So it's distance in kilometers along the bottom and cost in dollars around the side. And I'm going to spin this so we can see that. And now we need to go ahead and choose a scale. So my distances need to go from 0 to 400 kilometers, and I want to use up approximately as much of this graph as possible. This will be 0. I have 16 squares going across, so I can actually divide that up into 4 even chunks and say that each of those is 100 kilometers. Again, I don't have to write kilometers after each of these because I have labeled my axis. For cost, I need to go up to $140. I said there was 16 squares, so each square would be worth 10. But instead of writing 10, 20, 30, 40, that's a lot of writing, I'm going to write down every 20 as 2 squares. That way, it actually makes our graph look less cluttered and easier to understand. 120, 140. Now they didn't leave us a lot of room to put a title on here, but we always do want to put a title. And this one is going to be cost versus distance. Okay, so let's go ahead and plot our points now. I'm just going to scroll up a bit so we can see them. So 0 kilometers was $60. And I'm going to switch colors so that it's a little bit easier, hopefully, to see. So 0 and 60. So there's our first point on our graph. After 100 kilometers, the cost was 80. After 200 kilometers, the cost was 100. After 300 kilometers, the cost was 120. And 400 kilometers, the cost was 140. Now that is looking linear. Okay, I'm going to draw my line on there just to show that it does make a straight line. Sometimes we have to think about whether or not we want to connect the dots. In this case, we can, because distance and cost are both continuous. That means that there's a whole bunch of distances in between. All the decimals and fraction distances make sense, and so same thing for cost. Calculate the rate of change for this example. See below. Okay, so down here we have a formula for rate of change. And we are going to just skip down here for a second and take a look at this definition or formula. So we can use each representation above to calculate a rate of change. Make sure to always include your units when calculating a rate of change. We pretty much always want to include our units. This is a great formula. The rate of change is the change in the dependent divided by the change in the independent variable. Now that's pretty wordy formula. So how I'm going to write that in the future for shorthand, just to save time, is I'm just going to call it the rate. Change, the symbol for change in mathematics is the Greek letter delta, which is actually a little triangle. So I'm going to shorten my formula when I write it out. You'll see me write this: the change in dependent over the change in independent. So that's a little triangle meaning change. And that way I don't have to write out that big wordy formula every time. Okay, so here I'm going to practice that on F. So for this question, I'm going to calculate my rate, which is my change in the dependent divided by the change in the independent. So the change in the dependent variable, if we look up here, how much was this going up by each time? And it was always going up by 20. How much was the change in the independent? Well, we picked these numbers on purpose to always go up by the same amount to make it easy. So here I went up by $20 and here I went up by 100 kilometers. So make sure you include your units here. So I'm going to not write 20, I'm going to write $20, and then I'm going to write that's per 100 kilometers. And when I divide that on my calculator, I actually get 20 cents per kilometer, or $0.2 per kilometer. Why would we write the 0? Well, just because money-wise, we're used to seeing two placeholders for cents, not just the tenths, but we want to see the tenths and the hundredths. Okay, so that is our rate. Notice that it has the units, a dollar sign and per kilometers. The last part of this question is determine the equation. So the equation is how would you calculate your cost? So your cost would be that rate that we just found multiplied by the distance, plus we always have to pay that base fee of $60. Okay, so if you want to figure out the cost for any trip, you take the distance, that's how many kilometers you went, you multiply it by 0.2, and you add 60. Okay, so that is it for that question there. Now let's take a look. There's a few more examples. This is a bit of a longer section. Okay, example 2, which of the tables below represents a linear function? Justify your answer. Okay, so what we want to look at is how much are we creeping up by? In our Fahrenheit column here, we added 9, then we added 9, then we added 9, and so on and so forth. It was 9 all the way down. Now the question is, was it steady on the other side as well? And yes, it was plus 5, plus 5, plus 5, plus 5. So this one is linear. And it says to justify our answer, so we should actually type out a reason why. And I'm going to say linear because as C goes up by 5, F goes up by 9. So it's got a constant rate. Okay, let's take a look at this one. Oops, pardon me. Oh, geez. Pardon me again. Just trying to click on this here. There we go. Okay, so here our P or power is going up by 75 watts. Then it goes up by 225. Well, already I can see that these are not the same. Let's see if it was the same over here, +5, +5. Yeah, so it was the same on the left with our independent, but it wasn't the same increase on the right. So therefore it is not linear. And I'll give an explanation here. And that is because I is not going up by a steady amount. Sorry, I is going up, but P is not. So they both have to be going up by the same steady amount in order to be linear. Okay, example 3, identifying a linear function. Which one is linear? Justify your answer. So one of these is and one of these isn't. What's tricky is they both seem to be linear when you read them. Okay, so the first one talks about a new car is purchased for $24,000. Every year, the value of the car decreases by 15%. The value is related to time. Okay, B, for a service call, an electrician charges a $75 flat rate plus $50 for each hour they work. Okay, the total cost of service is related to time. So what I'm going to do is create a table here. And we're going to go 4 by 4. Sorry, 2 by 4. And oops. Let's try that again. There we go. Okay, so this one here we have time, and this would be time in years. Talks about the value changing every year. This one would be the value of the car, and that would be in dollars. So at 0 years, the car was worth 24,000. The next year, it had lost 15%. So we have to do a little bit of calculating there. So that means it's only worth 85% of its value. So 0.85 times 24,000 is 20,400. After 2 years, we have to take that 20,400 and multiply by 0.85 again to get the remaining value. And it's at 17,340. And then after 3 years, it would be at $14,739. So you can already see that this is not the same value that it's going down by each time. In fact, I've done the calculations on it to save us a little bit of time here. And to go from here to here, it lost a value of 3,600. Now it's okay to have a negative there. The question is it the same amount of negative each time? And in fact, it's not. Whereas here we are going up by 1 each time. So this is not linear. We've justified our answer by showing this table of values. Okay, let's do the same thing here for this service call. Man, this thing does not like to travel with me, does it? A little bit tricky there. I will just draw the table. It doesn't seem to like being moved around too much. Sorry about that, guys. Okay, so here's our next table. And this time it's going to be time in hours, not in years, because this is a plumber. So time in hours and cost in dollars. So after 0 hours, it still costs $75 to have your plumber come out. After 1 hour, we need to add $50 to that. So we have a $125 cost. After 2 hours, it's $175. After 3 hours, it's $225. How did I know that? Because it's $50 per hour. So $50 per 1 hour means that we've shown we have a consistent step here, matching a consistent step here. So this one is linear. And again, our justification is showing that information in a table. All right, here's our final example. Thanks for sticking with me. This is a long section. So example 4, determining the rate of change of the linear relation from its graph. So here, this time we're given the graphs and we're going to answer some questions about them. So what does the graph represent? Well, graph A shows the change in volume over the change in time when you're filling a water tank. I'm going to type that. So this is how the volume of water in a tank changes over time as it is, so it's filled. Okay, and I'm just going to squish that into this box here. Okay, this one shows how the volume of water in a tank changes over time. But what's the difference? This time it's as it's emptied. Slightly different scenario. You can see one of them is increasing the amount of water and the other one's decreasing the amount of water. And you can also tell by the title. So that's a good example of why a good title can really help people understand your graph. In this one, the independent variable is time in minutes, and that is actually true over here as well. Okay, the dependent variable in this one is volume in liters, and on the second graph, it's volume in liters as well. So that's the same for both graphs. Now the rate of change. Remember our formula for rate. So I'm going to write that out here. So rate is going to be the change in the dependent over the change in the independent. And sorry, I'm getting a little bit squished here, but I'm going to have to write like so. So this one changes 1,000 liters per 20 minutes. So how do I know that? Sorry, I scrolled up too far. You can't see the graph. If I just look at the change between these two dots here, they went up 1,000 and over 20 minutes. So that's where I'm coming up with that. That means that this tank is filling at a rate of 50 liters per minute. So notice that we have units on that. We're going to do the same thing over here. So the rate is the change in dependent over the change in independent. So this one, between this dot and this dot, it went down 2,000 liters and over 20 minutes. So I lost 2,000 liters. So I'm putting a negative in front of that. And that was over a 20-minute time frame, which means I'm losing 100 liters per minute. Now that makes sense because that's a faster rate than the other graph, and this looks like a steeper slope. Last question, what does the rate of change represent? Well, I kind of hinted at it in my last comment there, but this rate of change in each graph represents a speed. So the first one is the speed at which the water tank is being filled. And then the second one, the rate, represents the speed at which the water tank is being emptied. Okay, that is the last example for this section 5.6. Thanks for tuning in, and we'll catch you with our next one.